Okay, so in this video, we're going to be talking about modular arithmetic, and here are the readings. So Logic and Proof 19.4 and Fundamentals of Higher Math section 4. So make sure you've read those before you listen to the video. So we talked about modular arithmetic a little bit before, maybe not as arithmetic, but as a relation. So if A and B, say they're integers, if A and B have the same remainder, when divided by n, by some, usually a natural number n, we say that A and B are congruent mod n, and we write A equivalent to B, or congruent to B, mod n. Okay, so here are some examples, and in particular, some examples showing what we mean by modular arithmetic. So say we want to add 1 and 2 and see what equals mod 3. Well, it equals still 3, mod 3, but we usually want to write every number when we're in the mod 3 world as kind of its smallest representative. So we could write 3 or 6 or 9 or 0. They're all equivalent. They're all congruent mod 3, but we choose to write 0 here because it's the smallest number, smallest natural number that's congruent to 3 mod 3. Right? So 1 plus 2 is 3, of course, normally. And then we choose here the smallest number that's congruent to 3 mod 3. So we say that 1 plus 2 is congruent to 0 mod 3. 2 plus 2, similarly, if we are looking at it mod 3, we get 4, but the smallest number that is congruent to mod 3 is 1. We can also do multiplication, so that's again 4, so that's 1 mod 3. Let's switch systems, so let's look at mod 5. If we add 3 and 4 mod 5, we get 7, but we like to write 2. 3 times 3, we get 9, so we'll write 4 mod 5. And because 3 times 3 is equivalent to 4 mod 5, we can even talk about division here and say 3 divided by 4 is equivalent to 3 mod 5. And the book, Logic and Proof, says a bit more about this. And I'll say, but I do want to say something that's very interesting, all this modular arithmetic stuff. If we put here a prime number, then every number here can be divided by any other number in the system. It doesn't quite work if the number that we have here isn't prime, but if it is, it does work. And that's the beginning of number theory, and in particular this modular arithmetic stuff is very important for a lot of applications of number theory, like cryptography and stuff like that. Okay, so before we move on, I want to note that not only have we talked about this in class before, but it should be very familiar to you because we do mod 12 and mod 60 arithmetic all the time when we're talking about time. So, for example, if it's 3:42 p.m. and your friend says, oh, give me 30 minutes, I'll be ready in 30 minutes, then in your head you add 30 to 3:42, and we're really just focusing right now in this example on the minutes side, so it's not so important, the hours. But the hours, when we're talking about the hours, we're doing arithmetic mod 12, and when we're talking about minutes, we're doing arithmetic mod 60, right? Because 42, what's happening here that I want to illustrate is that 42 plus 30 is congruent to 12 mod 60. So when we add minutes, we're always doing arithmetic mod 60, and when we add hours, we're always doing arithmetic mod 12. So that's actually something that is very common in our everyday lives. Okay, so let's talk about some of the building blocks of modular arithmetic. So let's point out that basically everything works as it should. We can do arithmetic like we normally would. It's just a little bit weirder. So say we have a bunch of guys. We have A and B that are congruent, mod n, and C and D that are congruent, mod n. Then we can prove, though we won't here, but it is in the logic and proof book, that A plus C is congruent to B plus D mod n. So that works as it does in normal arithmetic. If we want to multiply them, nothing weird happens. We still have that A times C is congruent to B times D mod n. And we can also raise these guys to any power, of course. So we have this for any power that we would consider. Okay, so here's an example of a proof using modular arithmetic. So here's the statement. For every natural number n squared plus 2 is not divisible by 4. So I just want to say that this whole modular arithmetic stuff is really cool because basically statements like this that, I don't know, to me at least seem a bit opaque without modular arithmetic are so easy to prove with modular arithmetic. You just get for free all these interesting facts about numbers, and that's why people use this stuff to study numbers and have called that business number theory. Okay, so how do we do this? Well, let's start with n. So let's think about n. Well, before we do that, pause the video, think about how you would prove this. Even if you don't get anywhere, it's always useful to think about it by yourself before you listen to me tell you the answer, because then you'll be just naturally more interested in the answer, you'll remember it better, and so on. Okay, so how do we do this? Well, we're going to, as the whole lecture suggests, be thinking about this as doing arithmetic mod n. Okay, so let's look at mod 4. So let's look at n first and see what's possible. So for n, there are 4 cases of what n can be mod 4. So we can either have that n is congruent to 0 mod 4, that n is congruent to 1 mod 4, that n is congruent to 2 mod 4, or that n is congruent to 3 mod 4, right? So basically we're looking at the remainders that n can have when we divide it by 4. So there's these 4 possible remainders that n could have. Okay, now we just evaluate n squared plus 2 mod 4 and see what happens. So if we look at, let me just actually write some little annotations. If we look at n squared here, in this case, in case 1, then of course that's going to be 0 squared, which is still 0. N squared here is going to be 1 squared, which is 1. N squared here is going to be 2 squared, which is 4, which is congruent to 0. And n squared here is going to be 9, which is congruent to 1 mod 4. Okay, so there are really 2 cases for, well, there are 4 cases for n, but now 2 cases for n squared. Some of them have collapsed into each other. So there are 2 cases, n squared is 0 or n squared is 1. So in cases 1 and 3, we have that n squared is congruent to 0 mod 4. So n squared plus 2 is congruent to 2 mod 4. And in cases 2 and 4, n squared is congruent to 1 mod 4. So n squared plus 2 is congruent to 3 mod 4. And so what we see is that in no case that's possible, in no case at all, is it the case that n squared plus 2 is congruent to 0 mod 4, which would mean that n squared plus 2 is divisible by 4. So you can say, since in no case is n squared plus 2 congruent to 0 mod 4, n squared plus 2 is never divisible by 4, because being divisible by 4 is just another way of saying that you're congruent to 0 mod 4. All right, so that's the proof. So this is it for the lectures on this number theory section on LO 10. In the under like this module, I will put exercises that I suggest in both textbooks. And if you want any solutions, just leave me a message on the discussion board and I'll post solutions.